besides this signal integrity issues, there is one more problem associated with the dynamic circuits, which is cascading of dynamic gates in order to create a more complex structures. So here you can see one dynamic CMOS logic is cascaded with the another dynamic CMOS logic. Okay, so that output is connected to the input of the next dynamic logic. So during the pre-charge phase, okay, during the pre-charge phase, clock is 0. Okay, if clock is 0 means V naught and VDD goes to V out goes to VDD. Okay, so this is my clock. It has pre-charge and evaluation phase. Okay, so V naught goes to 1 during the pre-charge phase. Okay. And my V out also it goes to it remains in VDD, right? So let me assume that IN is making a transition from 0 to 1, okay, on the rising edge of the clock. So this will make my V naught to 0, right? And my since this is 0, D becomes turned off, and V out should be 1, right? So since A is making A 0 to 1 transition, V out has to be 1, right? So let me assume during the evaluation phase, ABC is 1. Okay, the V naught start to discharge. So if V naught start to discharge, okay, D gets turned off, and V out will remain in VDD. Has to remain in VDD, right? So this get discharged to this path. So V naught goes to 0. So D is turned off. So V out will remain in the same state, that is VDD. Okay. So this is what actually should happen, right? But you can see in the V naught, okay. So we can see in the V naught the actual V out, okay. So you can see there is a finite propagation of delay for the input to discharge output V naught to ground, okay. So so this will remain for some duration, which will turn on this D and C. Okay, C is already on. So my V out tends to discharge. Okay, so my V out tends to discharge. So till discharge, okay, and it cannot be recovered, right? It is not going to 0. Okay, so so after that V naught is going to 0. So which will turn off my D. So V out will remain the same state. Okay. So so therefore the current level will not be recovered. Okay. Since the dynamic gates which rely on the capacity storage in contrast to the static level, which have the DC storage. Okay. So del V is my lost charge. Okay. So these lost charge will lead to the reduced noise margin and potential malfunction. Okay. So in order to avoid this one, the transistor should be turned on when it is needed, and at almost once per the cycle. Okay. So in order to avoid this problem, we are going for the domino logic. And if you see, if I cascaded more number of transistors like this, which will tend to um, more glitches, the problem get worse because the delay are additive from the input to output. So another important problem of dynamic CMOS logic is capacitive coupling. So here you can see this dynamic CMOS logic is driving the static NAND gate. Okay. So here you can see there is a back gate coupling. Okay. Back gate coupling. That is, my output to input coupling. So the output get coupled with this input. Okay. So consider during the pre-charge phase, the clock is 0, and this x, okay, sorry, x1, y, okay. This y goes to VDD. So if this y goes to VDD means this PMOS is turned off. Okay. So due to the back gate coupling, what will happen is this y, that is the VDD, get coupled to this output. Okay, that is x. Okay, and it will tend to go low. Okay. So whenever this VDD value, that is y value, which is less than VIH. Okay. So what will happen? This will goes to 0. Okay. If it is goes to 0 means this PMOS turned on. Okay. If this PMOS turned on means the output goes to 1. Okay. So initially it is 0. Okay. Since there is no charge, but since this value start to reduce via this capacitance, it will tends to turn on this PMOS and will make this output from 0 to 1. Okay, transition from 0 to 1. So this will result in the incorrect output. Okay. So while designing this dynamic CMOS circuit, we have to take a special care to minimize this capacitive coupling. So since we have this static gate, it will also consumes a small amount of static power. Static power is dissipate.